All right, so if you can't hear me, I can put the mic on. You guys good back there? Okay, cool. All right, so we're going to start with, so 49, 50, 51, 52, 53. They're all about the same thing, right? So solving quadratic equations. On the final, memorize the quadratic formula, but if you have done these, solving them graphically, you can do that. Factoring may or may not always work, so just whatever works for you. I mean, that's the thing about multiple choice. We're not checking how you got the answer, so whichever way that you are comfortable solving the problem, just as long as that you know that for solving quadratic equations, the first thing you need to do is set it equal to 0, right? Okay? So in order to do that, the first step we would do is bring the 7 to the other side so that we have a quadratic equation set equal to 0. Okay? All right, and we'll go ahead and use the quadratic formula. So I told my students I'd give them extra credit points if they knew the little song that goes to Pop Goes the Weasel. All we figured out is that it's all over 2a. We couldn't figure out the rest of it, so anyway. Okay, so that's the quadratic formula. Oops. All right. So in this case, we have x equals -5 plus or minus the square root of 5 squared minus 4 times 2 times -7 all over 2 times 2. All right. With these problems, so in the beginning of the semester, right, we were just looking at real solutions. Now we can also find complex and imaginary solutions, so you want to make sure that you can do both, right? So I'll go ahead. This one works out to be -5 plus or minus the square root of 81 over 4. Do all of the calculation, right? And so then that actually gives us two solutions. And we'll go ahead and take the square root of 81, which is 9. So two solutions, -5 plus 9, all divided by 4, or x equals -5 minus 9 divided by 4. All right. And so that works out to be x equals 4 over 4, or 1, and x equals -14 over 4, or -7/2. Okay? All right? Okay? So again, knowing the formula will help. Much easier, even if you can factor, it's easier to use that one. Okay. Good? Okay. All right, so 51, I'm not going to actually go through it all the way because, I mean, it's just going to be a lot of the same thing using the quadratic formula. But I just want to make sure that you know, you don't want to set that y equals 10, y minus 3 equals 10. Right? You want to actually go ahead and distribute it so that you have a quadratic equation. So this would be y squared minus 3y equals 10. And then we would have y squared minus 3y equals 10. And then the same thing, y squared minus 3y minus 10 equals 0. And I think that one you can actually solve by factoring. Okay, so I think it's y minus 5, y plus 2. Equals 0, okay? And so then your two solutions are y equals 5 and y equals -2, okay? But you just want to make sure, don't make the mistake of trying to split that up. If it were set equal to 0, which we'll see one in a second, that's like that, then you could separate it as y equals 0, y minus 3 equals 0. Okay? All right. So let's look at number 53, which is one that has complex solutions. And I'll slow down a little bit with this one. I just want to make sure we get to the end of it. Okay. Okay. So one of the key things here with these problems, with multiple choice, you want to be able to put the solution in its most reduced form. Okay. Otherwise, you'll not see the answer there. Okay. So the solutions will always be in the most reduced form. So you want to get it so that it looks something like that. Whoa. Wait a minute. Those aren't the right answers, are they? Okay, so forget these answers. We'll just work the problem out, and then so the correct answer on yours should be C. Does everybody have that? Do your solutions look like this? Like this? Okay. All right, so the actual solution would be C, negative 2 plus or minus I, the square root of 6 over 2. Yeah, we skip 52. We're going to skip 52 is just another quadratic, solving the quadratic equation. So this is 53. Okay? Right, but so is this one. Okay, so, all right. Okay, so this should be the answer for 53. All right, and we'll work through it. Oops. Okay? All right. So again, we want to set this equal to 0. So 2x squared plus 4x plus 5 is equal to 0. Okay? And then we'll use the quadratic formula again. So x equals negative b, which is negative 4, plus or minus the square root of 4 squared minus 4 times 2 times 5. Okay. All over 2 times 2. All right. And so you get x is equal to negative 4 plus or minus, if you figure out what's underneath the square root, you should get that it is negative 24 all over 4. Right? And so that right there tells you, right, so if we hadn't been talking about complex solutions or imaginary solutions, we would just stop and say there were no real solutions. Okay, so there are no real solutions because the discriminant, or what's under the square root, is negative. But there are complex solutions. Okay, and so we don't want to leave it like that because we know that we can rewrite this as the square root of 24i squared, right? Okay, so I'll put up here, I squared is equal to negative 1. So we rewrite it. Okay? All right, so we basically what we did is we took negative 24 and we broke it down into 24 times negative 1. Replace negative 1 with I squared. Okay? All right, and so now we can reduce it further. We can say, all right, well, this is negative 4 plus or minus the square root of, and again, this is what I was saying, you could leave it like this, but we wouldn't want to. So 24 is 4 times 6, I squared all over 4. Okay. And so, right, we can bring a 2i outside of the square root, the radical. And we're left with 6 underneath it, and so we have that. Okay. So negative 4 plus or minus 2i times the square root of 6, all divided by 4. All right, but again, you want to reduce it as much as possible. Okay. And so we would do that by dividing through by a 2. Okay. So if we divide through, and I'll go ahead and factor it out. So we have negative 2 up here would be 2 plus or minus I, the square root of 6, all over 4. So it's technically what you're doing when you're canceling out. And then we can cancel out a 2, and so we're left with negative 2 plus or minus the square root of 6 all over 2. Okay, so that should be C on your review sheet. Okay? Which you can't see. Right? Okay, so you definitely want to make sure that you go back and look at some of the problems. The one that was right before that, number 52, has complex solutions too, is what someone said. So make sure that you are able to do that. Again, being able to reduce it to the most reduced form. Yeah, so on this one, 53, the answer is C. Okay?
When you simplify, can you show that again, please? I'm sorry. When you simplified from negative 2 times 2 plus or minus I times the square root of 6 over 4, you simplify that to negative 2 plus or minus I times square root of 6 over 2.
Got. Okay, so basically we factored a 2 out of the numerator. Okay? So here, 2 out of a numerator, and the divided in the denominator. Okay? All right. number 54. Okay. All right. So in this question, number 54 and number 55, you're dealing with questions probably that you remember from the homework where you used an equation that looked like this. Okay. All right. So make sure that you're a little bit familiar with that quadratic equation. Right. So it models if you throw something up in the air and then it falls back to the ground. The x value is the time, right? And it's, in this case, we're calling it h of t. I think in the homework they might call it s of t, but it's the height, okay? So in this case, it says in an experiment, a ball is thrown upward with an initial velocity of 120 feet. So we see that here, right? It says let h be the height in feet of the ball above the ground t seconds after it was thrown, okay? Now, in this case, the initial height we're talking about is 0 because what we're looking for is the time required for the ball to return to its point of departure. Okay, so meaning we're counting 0. So if I throw the ball from this height, we're counting that as the starting height. Okay. Okay. So in order to find the time required for the ball to return to its point of departure, we're actually trying to figure out when it drops back to the starting point, or so when this is set equal to, when the height is equal to what? To 0. Okay? So that's the equation we're trying to solve, when h is equal to 0. Right? And so then we can just solve this, and actually we don't need to use the quadratic formula in this case. Right? We can factor out a t. We can rewrite that as negative 16t plus 120 equals 0. Okay. Right. And so then we actually can get two solutions. The first solution would be t equals 0. Right? So that corresponds to after 0 seconds. So the point of when you're throwing it out. So that makes sense. At t equals 0 seconds, the height is 0. Right? But then the second one, if we solve that, just like we would quadratic equation. So we have that, and we get t equals 120 over 16. Okay, and so that actually comes out to be 7.5 seconds. Okay, so that means after 7.5 seconds, the height is back down to 0. Okay. So, we wouldn't put t equals 0, right, because that's the starting point. Okay, t equals 0 means after 0 seconds. So after 0 seconds, then after 7.5 seconds, it gets back to wherever it started off from. Okay? All right? Then the second question that is dealing with this equation, number 55. Right, so again, we have the same equation. Again, the initial velocity, or in this case, the initial velocity is 160 feet per second. Right? But the same idea, that h represents the height from the point of departure, t represents the number of seconds. Right? Now we're trying to find the maximum height of the ball. Okay? So if you kind of think about, this is the graph of this would be a parabola that opens down. And so we're talking about what is the highest point or the vertex, which we know how to find the vertex, right? Okay? So you can think about it as being, a parabola that looks like this. And this would be the place where it started, and this would be, I shouldn't have drawn those parts at the bottom. So, okay? But we're looking at this point right here. Okay? We're looking for the vertex. Yeah, sorry. Okay? All right? But we're not looking for the entire point, right? So the vertex is going to be a point that in terms of this equation would be t comma h, where t is the number of seconds and h is the height. What is the question asking us to find? H, the maximum height. Okay? Right. Okay? All right, so find the maximum height. So you want to pay attention to definitely the directions too. All right, so we're going to use the vertex formula. And so in this case, it would be h of negative b over 2a. Okay. Okay, so we'll still need to find t, or the x-coordinate, right? And then substitute it back into the equation to find the h, or the height. Okay, so this would be negative b over 2a. In this case,
negative b over 2a equals the x of the vertex.
Right. Exactly. Okay, and so that comes out to be, let's see, comes out to be 5. All right. Okay, so it reaches its maximum height after 5 seconds, but the maximum height would actually be the equation evaluated at 5. So negative 16 times 5 squared plus 160 times 5. Okay. And I think if you do all the calculations, it comes out to be 400. And that would be A. Okay? Right? So easy questions. Right? Questions like this, I mean, as long as you read what it says and you try to relate it back to, I mean, we spend a lot of time talking about quadratic equations, right? And so, you know, think about what you know. We know how to find x-intercepts. We know how to find the vertex. Okay, so you always want to kind of think back to what you know, right? Okay. Good? Now these questions where you're given the graph, okay, these questions shouldn't take too long. I mean, once you understand what they're asking, you just use the information from the graph, okay? So in this case, I have a quadratic, or I have a parabola, and I'm actually asking, where is this parabola? Where is x squared minus x minus 12? Where is it greater than or equal to 0? Okay, so in some of the homework problems, or maybe examples you've seen in class, we phrased it as, where is it positive? Where is f of x positive? Where is f of x greater than or equal to 0? It's all the same question, right? The nice thing is with the graph, we don't have to do a whole lot of figuring out, right? Okay, so if we look, I basically want to know, where are the y values? This is saying, where is the graph f of x greater than or equal to 0? Where are the y values positive? Okay, so we can see that we're talking about this part of the graph, right? So that part of the graph and that part of the graph, right? You see that? Because in the middle, this part of the graph, the y values are negative. Okay, right? Okay, key thing here, because we have greater than or equal to 0, we're also talking about where is the graph, or where is f of x equal to 0. And so that means my answers are going to have brackets. Okay, all right, good. Okay, so now what we need to know is, where are the 2 points where the graph goes from, and remember, we're always talking about, with these questions, we're talking about defining the answer in terms of x values. Okay, I think sometimes that's the part that gets a little bit confusing. So we're talking about, what are these x values where f of x is greater than 0, right? And equal to 0. Okay, so right. So we have this part here, which is negative infinity all the way up until we get to negative 3, close bracket, because we're including at negative 3. Right? So at that point, the graph is f of x is greater than 0. But then also from 4 to infinity. Good. Okay? All right? Okay? Again, using brackets because of it's greater than or equal to. Right? If it weren't greater than or equal to, then we would use parentheses. Right? Okay? Okay? And then number 56 is 57, sorry, is similar, right? But a little bit easier even, because it's multiple choice, right? So you don't even have to do a whole lot of thinking with that one. Oops. Okay. So now we're talking about a parabola that opens down. This time, because we're just looking for the values where it's greater than 0, okay? Not greater than or equal to, I know that my solution, we're talking about parentheses, all right? So really, only one of the solutions makes sense. Well, could always be none of these, so you got to think about that. But so really, we're talking about the part here, right? We're talking about the part of the graph, right? Again, where the y values are positive. So we're talking about the graph that's in between this point, whatever that is, and this point, whatever that is. Okay? So which one of these solutions looks like would probably match that interval? D.
So on the one before that, you're looking at everything outside. You're not looking.
Well, the reason I was looking at it, so it looks like, right. So the reason I was looking at everything outside on that one was not because the question so much changed in terms of, I mean, we're still looking for where the graph is positive or where they're greater than or equal to 0. What's different about this one and the one that we just did, or the next one, is this is a parabola that opens up, okay? And so at the points where it's outside of, and it's this particular parabola, where the graph is positive happens to be outside of the two x-intercepts, okay? So that's,
if it were to be facing the other way downward, then it would have been the same way. Everything inside.
right, okay? All right, so yeah, so because this one is facing downwards, and also because where it's located, all right, so I don't want to generalize, because in some cases you could have a parabola that sits entirely below the x-axis or entirely above the x-axis, and so then your solutions would change. But in this case, because the parabola is opening down, all right, and it's sitting part up and part below, right, then the interval that we're talking about is between the x-intercepts, and so the answer would be D, okay? Let me say this too. You want to make sure that you look carefully as you can. I know this one doesn't come out quite right, but if you couldn't tell by looking at the graph and you were concerned, you could also find the x-intercepts, right? You could use the quadratic equation, right?
So if
Okay.
you were to say then, like on the first one, the parabola opening up, or up, right, facing up, not down, and it's everything outside of the x.
In most cases,
In
but
most cases.
there is a scenario in that case where the parabola could be sitting completely above the, it's always positive. Okay, so you want to be careful with that. But yeah, I mean, in general, this is what you're going to see. Okay, so, okay, if it has two x-intercepts like that, then, all right. Okay. We are on 58. Okay. Okay, easy question, all right? Which one of the following functions is a polynomial? Right. So in general, polynomial functions look like this combination of different terms that all have to do with a exponent and x, right? So the only one in a positive exponent. So we really don't want anything that's a square root. We don't want anything that's a fraction, right? Well, the coefficient could be a fraction, so meaning these could be 1/2 or 1/4 in front of the x, but where the x is actually part of the fraction. No negative exponents like in D, and no exponential functions like in E. So the only one that would be a polynomial function here would be A, right?
Now, because it has more than two exponent, or more than one exponent, doesn't that make it a trinomial, or something other than a
polynomial?
just
Okay.
means many?
Yeah. Okay, so polynomial is the general term. Okay.
Not a binomial. A
Right.
binomial is one exponent. Is that right?
No, it has to do with the number of terms. Okay, so binomial is like x plus 2, x plus 3. So polynomial function, and let's just write so polynomial function, right? If you remember, looks like this. Just so that you have it. Sorry, I will. Hold on one second. Okay. Okay. All right. Okay. So it would be A. All right. What is the x-intercept? How would you find? I'm sorry, the y-intercept. How do you find the y-intercept for any type of function, really? You're looking for the point where the x value is 0, right? Okay. So we're looking for some point 0y. So how would we find that? Set x equal to 0. Okay, so we plug in 0 for x, so f of 0, and this would kind of be pretty easy to see that that would be 0 plus 0 plus 3, which is just 3. So the x-intercept would be 0, 3. And I think, the y-intercept, you would write it as just y equals 3. Okay? Right? So y equals 3 is the y-intercept, and then the domain for any polynomial function would be negative infinity to infinity, or all real numbers. Okay, that's what makes it polynomial functions. The domain, those values of x for which the function is defined. We could either write it like this, or we could write all real numbers. Okay? Right. Okay. Okay, number 59. Oops. Let's start with that one. Okay. So what is the degree of the polynomial function? What is the leading coefficient? Okay, so the degree for this one is actually 5, right? It has to be the largest exponent. Okay, so you want to make sure you're looking at it. It's not necessarily written in descent, or maybe not because of line. But think about a parabola. How many x-intercepts can a parabola have? 2. It can have 2, the most, right? At most it can have 2. It could have 1. It could have none. Okay, but the maximum number of x-intercepts it can have is 2. All right, and so in general, a polynomial function, I'll write this up here. Can have a maximum of n x-intercepts. And I should put with degree n. That would help. Okay, so a polynomial function with degree n can have a max of n x-intercepts. Okay, so if we have a third degree polynomial, okay, what is the, at most, how many x-intercepts can a third degree polynomial function have? 3. So B. Okay. All right. And then related, okay, the turning points, right, so a polynomial function with degree n can have at most, now we say n minus 1 turning points. Okay? All right, so you want to make sure that you look at those, right? Okay? 1 less. Okay, so n minus 1. If the degree is n, then the most it can have is 1 less, or n minus 1 turning points. Okay, so if at most, how many turning points can a third degree polynomial function have? 2. Okay? All right? All right. And so now we can kind of apply that in 62. All right? So again, this question, all right, well, we'll pull up the answers in a minute. Let's just look at the graph first. Okay? Okay? So this question should be very easy, and it shouldn't take, this should be a really quick question. All right, so we have a polynomial. It looks like it might be what degree? It looks like it might be 3, right? We don't necessarily know for sure, because maybe we just have a snapshot of it, but it looks like it's a cubic, all right? So what we want to know is, given the graph, what is the minimum degree, okay? And so the minimum degree would be, so you're, hold on, let me just fold this. Okay. Of those choices, the minimum degree would be 3, right? Because we notice here we have 1, 2, 3 x-intercepts. Okay, so that kind of takes out that it could be degree 1 or 2. All right, and then it has 2 turning points. Right, 1, 2 turning points. So then we think that the minimum degree could be 3. It could be more, depending upon if we looked at the, if that's just a piece of the graph. But we're looking for the minimum degree. Right? Okay. So again, easy question. All right, number 63. All right, so which of the following points is a turning point? Right, so turning points, remember, are the points where the graph changes from either increasing to decreasing or decreasing to increasing. Okay, so this graph, if you look at it, it's increasing until it gets to this point up here, and it looks like the coefficients of that point are negative 2, 4. And then it's decreasing until it gets to this other turning point down here, and the coefficients of that would be 2, negative 4. Okay? All right, and so which of the following points is a turning point would be C. Okay, so C, negative 2, 4. Okay? All right? Then the next question says 64, which of the following values is a local minimum? Okay? So same graph. But now we're looking at the looking for local minimum. Right? Now again, a local minimum is a point where, so it's kind of thinking about it, it might not be the lowest point on the entire graph, right? Because if we look at this graph, it keeps going. So we know that it really doesn't have a minimum. But a local minimum says that I can call this point where it's kind of a dip, that point is still important, and that is going to be a local minimum, right? And so the key thing here is we're talking about the y value, all right? Okay, because if you notice, your choices are not points, they're just one value, right? So you want to put the x value, y value. All right, so that one would be, that point is, we already said, 2, negative 4. So the local minimum is negative 4b. Okay? All right? Okay, and then this would be a local, right, maximum. Okay, up there. All right, one more question with this graph. You guys hanging in there? I know it's a long review. You know what, though? The final is not nearly as long, so, yeah. Yeah, well, yes.
Our brains would be crying.
Yeah, I think our brains would be crying. Okay. All right, so same graph, but now we want to figure out where the function is decreasing, right, and use interval notation to determine that, right? Okay, so again, we're looking at our turning points as sort of the cutoff points, because those are the points where the graph changes from increasing, decreasing, 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 right? So those are going to be our two endpoints. And so the way that we figure this out is we're going from left to right, and we think about it like we're kind of tracing the graph. So going from the leftmost point, it's increasing until it gets to this first turning point, which we said is, let's write that down again, negative 2, 4. And then it starts to decrease, right, until it gets to negative 4. And then it starts to increase again, okay? And so we're looking for where the function is decreasing. So we're talking about this part of the graph right there, okay? And so that would be which answer? D, okay? It would be, because we're defining it in terms of the x values, right? Again, we're talking about the interval. We're defining where it's where it's decreasing in terms of the x value. So this would be between negative 2 and 2. The important thing here is when you're talking about increasing intervals of increasing and decreasing, you always use the brackets, okay? Right? Right? Okay. Okay, so let's talk about 66. We won't spend a whole lot of time on it. Okay, so here you're not really given a picture. You know, obviously graph it if you need to. One thing that you can think about is that this is a parabola, right? So, okay, I'm going to graph this for you. Just pretend like, you know, I'm your graphing calculator, right? But I know that there's a y-intercept there, and I think it's over here, okay? Okay, so it's a parabola that opens down, right? It does not look like a good parabola, but you get my point, okay? So what I'm talking about, the turning point for a parabola is the vertex, right? Right? At the vertex, So from here to here, this parabola from negative infinity to the turning point, it's increasing, and then it starts decreasing from the vertex to positive infinity, right? So even though I don't have a graph in this picture, you have to use what you know about quadratics and what you know about parabolas. I know that it's a parabola that opens down, okay? I know that the vertex is the highest point, and at that point, the graph changes from increasing to decreasing, or decreasing to increasing. So what I would have to do here to solve this one is figure out the coordinates of the vertex, and that's how I would figure out what the intervals were, all right? So we would use the negative b over 2a again for the x coordinate. So this would be negative 4 over 2 times negative 1, which is 4 over negative 2, which is negative 2, okay? I don't really need to know the y coordinate, right, because we're defining, we can find it, but since we're really talking about intervals of increasing to decreasing, I'm really just talking about this interval here, okay? And so how would I write, what is that? So where is the graph? It's increasing from negative infinity to negative 2, okay? All right. You know, if you have a graphing calculator, this would be the place where on the test you would graph it, although I'm pretty sure in most cases you're given a graph, okay? So I don't think that you would have to do that.
Graphing calculator, do you have?
Well, I don't mean, just to kind of get a picture. Yeah, just to get a picture. But you know, you could look at this and know, you should kind of know that that is a parabola that opens down. And so you're talking about the vertex. And if you can sketch that for yourself, then you can talk about where it goes from. And then you just think about, all right, well, if it looks like that, then I know that as I go from left to right, I'm talking about that it's increasing until I get to this point, and then it's decreasing, and that point is the vertex. Go ahead.
Can we use the graphing function on our graphing calculator?
Oh, no, you can't. Can you?
No, we can't.
No, you can't. I'm sorry, you're right. Yeah, you can't. So you're going to have to sketch it. Yeah. But, that's okay. I think that you can figure out what the graph looks like. So, yeah. So I take that back. Yeah, sorry. No, you can't do it on the final. Yeah. But I think in most cases you're given, for something like that, you're probably given the graph. Okay? All right. Now, in 67, you would not be given the graph. But that's okay. Okay? So I know in this case you wouldn't be given a graph. You might not even be given a function. You might just be given that you have a degree 4 polynomial, that's leading coefficient is positive, and just given that information, you should be able to answer what the end behavior is. Okay? So one of the things that you want to recognize with this is that the degree is an even degree. Okay? And so this behaves like a parabola or quadratic. Right? So if you remember that section where you did some classifications with even and odd degree polynomials? You want to use what you know kind of about parabolas and even degrees polynomials to answer this. All right. So because this is a even degree, x to the 4th, I know that the end behavior the same end behavior happens at both ends. Okay. So in the same way that parabola, either both ends open up or both ends open down, it's the same thing with the 4th degree polynomial too. Same thing with 6th degree, 8th degree, okay? So in this case, the only thing that's going to tell me whether both ends are opening up or both ends are opening down is what? Leading coefficient. And the leading coefficient is positive, okay? It's a positive 1, right? So in the same way that a parabola with the leading coefficient that's positive opens up, right? The same thing is going to be true about degree 4. So it would be an answer A. Okay? 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 All right, so again, you have to kind of go through, this is more of a thinking question. You have to think about the relationship between even degrees. But like I said, you don't even really need, I wouldn't even have to give you the rest of this polynomial, and you could figure that out. Okay? All right. 68. All right, so this is a perfect example. right? So similar to 67. Okay, so now this one has a odd degree, right? It's to the 5th power. This behaves like a line, right? In the same way that if you think about a line where the leading coefficient, you see that? The leading coefficient is positive, right? What does that line do?
It flips upward or positive.
It's increasing, right? Versus decreasing. Okay? So this is where A is greater than 0, and this is A is less than 0. Okay? So the same thing is true for 3rd degree, 5th degree. The thing that tells me how it behaves at the end. So, okay, one thing, the end behavior is different at different ends. When one rises, the other falls for an odd degree. But which tells me which one is the leading coefficient is negative. Okay, so since it's negative, it behaves like the line that has a negative slope. Okay, so we would say that this rises to the left and falls to the right. Okay? Right?
So yeah, if it was positive, then it would just be the opposite, right?
So if it's positive, it would behave in the other way. Rise to the right and fall to the left. Okay? So again, these types of questions, you know, it's not, shouldn't take too long if you kind of know those, you know those things about polynomial functions. Okay? Not a whole lot of calculation type stuff. Yes?
The exponent does matter, right? Like if it's even,
Say it again.
the exponent does matter. Like
Yes.
if it's even, they're both
Right, so the exponent, basically you can kind of separate it into an even degree or an odd degree, okay? So if it's an even degree, the end behavior is the same for both ends, okay? It's like a parabola. They either both open up or they both open down, okay? If it's an odd degree, then it's opposite, okay? Okay. So this should be a giveaway, right? Which one would this be? So polynomial functions are things that have kind of smooth, they're defined on the domain of all real numbers, no breaks, okay? So really that would just be 3, right? Here we see a break. Here we see these little corner, not a smooth corners. So like kind of like how absolute value functions behave, okay? And 2, it's not defined on the whole, the domain is not all real numbers, okay? So your only option there is 3, all right? Okay. Complex numbers. Okay, let's all exhale. We only got like, I think we're only going to 90. Yeah, because let me just say here, 6.3 is not going to be covered, so the last 2 numbers, we don't need to do the last 2 problems on we won't do the last 2 problems on the review, so we only need to get to 98, so we're almost there. Not really. Okay. All right, so these with the complex numbers, you want to think about how binomials behave with the whole, you know, combining like terms, using the distributive property to multiply. So in this case, this might look a little bit different because it's not actually in complex number form yet, but we'll do that first. So again, the key being that I squared is equal to -1, right? So we could rewrite this as 3 minus the square root of 36i squared plus 2 plus the square root of 16i squared. Okay, good with that? Okay, and so now we can take the square root and we have 3 minus 6i plus 2 plus 4i. And so then it's pretty easy. Yeah.
Will it mess you up if you factor them out first?
If
Because I didn't square it, I just got the square root, then put I behind, because it's a negative regardless.
so you're saying if you just went straight from here to here?
Yes, ma'am.
Yeah, I mean, that's fine. No, I'm just doing it just to show you. Yeah, you could go straight from here to
I was just saying,
this way.
because you
Yeah.
may have a reason.
No, I mean, as long as you don't forget the I, you know, and you don't forget to take the square root, yeah, okay. Okay. All right. So now we have a simple problem where we just need to combine like terms, which we can do. So we'll combine the 3 plus 2, and then minus 6i plus 4i. Okay. All right. And so in that way, it behaves like binomials, right? So we end up with, is that right? 5 minus 2i. Okay. Okay. All right, we'll let's skip down to 71 just because it's not too different from 70 part 2. Okay, it's still going to be multiplication, but I just want to make sure that we don't make a silly mistake. Okay. All right, so 70 part 2, we're multiplying the two complex numbers. We're going to do the same thing, but we're just going to do 71. Okay. All right, because what I don't want you to do is if you had something like 71, that you would just say 1 plus I squared, right? We don't do that. Okay, we don't just square each of the terms. So this is actually 1 plus I times 1 plus I, okay? And then you have to multiply them together just like you would multiply a binomial, right? So however you remember doing it, if you use FOIL, whatever, just make sure you multiply everything by everything, okay? So we would do 1 times 1 is 1, plus 1 times I, which is I, times I times 1, which is I, plus I squared. Okay? Okay, good. And so step ahead of me there, we combine the I, so it's 1 plus 2I. I squared is -1. Okay, so you want to make sure, remember the goal is to have a solution or have an answer that's in the form a plus bi, okay? So if you have I squared in your answer, you haven't finished. Say it again. Well, what are we going to do with the -1? We're going to do 1 plus -1.
You said multiplying it by the I squared to get it from I squared to negative.
Well, no. So I squared is just equal to -1. Okay, so that's what we're doing. We're going to see, we're just rewriting I squared. I squared is equal to -1, so we've replaced I squared with -1, and now we'll combine the 1 and -1, which is just 0, so the answer is 2i. Okay? All right? Okay, so again, if you do this and you have an I squared in your solution, then you're not done. You want to make sure that it's in this form. Okay? All right? Okay. 72. Or, yeah. Okay. All right, composition of functions. All right. The key thing with these, and we're going to do both of these examples. The key thing with this is that this little symbol, f composed of g of x, it's basically creating a new function using these two functions. But what helps us to figure out what we're talking about is that it's equal to this. Okay? So f composed with g of x is equal to f of g of x, because then we can just look at it in the same way where, so it may not mean a whole lot yet, but you approach this in the same way that if I said evaluate a function at a point x equals 1 and you did f of 1, right? Or the one I think we did earlier on the sheet where it was like evaluate the function at the expression a plus 1, okay, where you substitute in a plus 1 for values of x. It's the same thing with the composition of a function. This means that everywhere I see x in the function f of x, I'm going to replace it with g of x, okay? All right? So in this case, I have x squared minus 1 is f of x, and g of x is x plus 2. So what I'm going to do is I'm going to evaluate the function f at g of x, which is x plus 2, okay? And so what that's going to be equal to is now I replace x with x plus 2. Okay? And so we have that, right? And then we can simplify it so that we get x squared plus 4x plus 4 minus 1, which is x squared plus 4x plus 3. Okay? So f composed with g of x is this new function x squared plus 4x plus 3, which we created by evaluating the function f of x at g of x equals x plus 2. Really not harder than that. Main thing is that it's not multiplication. All right, so when you see the open circle, it's composition, it's not multiplication of the function. Okay? Okay, so you can have a question like that, or you can have a question like this, where instead of finding the function, we're actually evaluating, there we go, evaluating the composition. So find f of g of 1, right? So what we're going to do, it's the same thing, it's still composition of functions. But instead of going through, I mean, there's two ways that you could do this. We could actually find f of g of x and then evaluate that at x equals 1. But we're just going to do it just going straight. We're going to evaluate g of 1 first, and then we're going to evaluate f of g of 1. Okay? So the way I read this is that I start with finding the function g of x evaluated at x equals 1 of g of 1, which would be 3 times 1 plus 1, which is 4. Okay? And now I'm going to take that, this value, g of 1, and I'm going to evaluate f of x at 4. Okay? And so that would be the square root of 4, which is 2. Okay? All right. Questions on this? Are we good so far? All right. Okay. Now to make it even more interesting, good. Look at this question. Again, composition of functions.
So that's what those are called, the composition of functions.
Okay, composition of functions, yeah. All right, so now I want to find f composed with g of 4. And again, this is equal to f of g of 4, okay? And I write it like that. Sometimes it's a little bit easier to see what you're actually going to do, okay? Because what that tells me is that I'm going to go and I'm going to find g of 4, and then I'm going to plug whatever I get into f of x, all right? Okay, so how do I find g of 4? Okay. Very good. Okay, so basically I'm looking for the y value when x is 4 on the function g of x, okay? And so that would be correspond to this point right here, and that looks like -3, okay? So g of 4, so this point is 4, -3. So g of 4 is equal to -3, okay?
So if it was g of f, then it would be evaluating it at 4, or a different point on the f graph,
So
right?
if it were g composed with f,
Yeah.
then you would find f of 4 first and then g of 4, okay? So the way you kind of go inside out, you start from the inside. So I start here with g of 4, find that value, and then I'm going to use that, right. Okay, so now I'm going to find f of g of 4, which is f of -3. And now I can use the graph. So where x is -3, that point right there, what is f of -3? 0. Okay. Okay, so then that tells me f composed with g of 4 is 0. All right. Sorry. Okay. All right. So those are 3 different types of problems about composition of functions. They all use the same idea, right? The idea of composition of functions, but there's just different types of problems. So you want to make sure that you know, I mean, hopefully when you're reviewing for the final, you're not just doing one problem. I mean, if there's a problem on the review and you are like, easy, I don't need to look at that anymore, fine. But if you struggle, then you go back and you do 5 or 6 of the ones that you struggle with, okay? Because you know, there's a lot, like with this one concept, there's at least 3 different types of questions you could see. Okay? All right. 75. Ooh, let me see all those. So which one of the following statements is false? So these are about inverse functions. Okay? So a couple of things, right? In order for a function to have an inverse, the function has to be a one-to-one function. Okay, one-to-one. Remember, a function means that each x value is only assigned to one y value. One-to-one means it goes the other way. Each y value only has one x value. So any one-to-one function has an inverse. Okay? So that's true. The graph of a function and its inverse are reflections of each other about the line y equals x. That's true. I don't know, you may or may not have covered that in class, but that's true. If you look at the graphs of the function and its inverse, they are the reflections of each other. Okay? The graph of a one-to-one function passes the horizontal line test. Remember, the vertical line test is the one you use to check to see if a graph is, to see if a function, see if a relationship is a function, right? We use the vertical line test to see if it's a function, horizontal for one-to-one. Okay? And this last one here, the composition of a function and its inverse, by definition, it is the identity function. Okay? And so you might have seen some examples in class where you composed a function and its inverse, and you get the identity. So the one here that's not true is D. Okay? The inverse of the function is not always 1 over the function. Right? Okay? All right. All right, more likely that you'll have a question like this, though. Okay? So given the function f of x equals 3x plus 6, we want to find the inverse. Right? Okay. Scoot along a little bit. Okay. All right, so we'll just do one of these. There's 2 ways that you can do it. One way is you can kind of talk through it. We find the inverses by undoing sort of the operation. So if I were going to talk through this one, I would say, all right, well, f of x is equal to the function where I take x, multiply it by 3, and add 6. So the inverse of that would be undoing the last thing, starting with the last thing, undoing that, and then undoing and working backwards. So if I'm adding 6, the first thing I would do would be to subtract 6 and then divide by 3. Okay? So it would be C. If you have a hard time with that, the other way that you can do it is remembering that xy is a point on, then yx is on f inverse of x. Okay? And so what we would do there, what that would help us do is say, okay, so if f of x or y equals 3x plus 6 is the original function, then the inverse, I would switch these for the inverse. Okay? And then solve for y. So on f inverse of x, the x and y are switched. And so I would say that this is x equals 3y plus 6. Okay? And then I would just solve for y. And that would give me the inverse. All right? So solve for y. And we would do the same thing as we would come up with the same thing. So subtract 6. And then divide by 3. And y equals x minus 6 over 3. Okay? So however you get to it, you get to the answer just... okay, so it would be 3. All right? So... yeah, so it's not too different. You could do the same thing. You really only have 2 operations for 77. Is C. Okay, so all right, we'll look at it real quick. All right, so 77. Okay, so in this case, you're taking x, adding 2, and then taking the square root. So to undo that, what would be the first thing that you would do? Square it, and then subtract 2. Right. Okay. All right. So you're always thinking about undoing the last thing first. So it would be the square root would be squaring it to undo the square root and then subtract 2. Okay? All right, so let's look at 78 because I want to make sure that we get to the problems on exponentials, right? This one is kind of like the one you did earlier in the review, okay? The key with this one is remembering that on the inverse, if xy is a point on the function, then yx, the y and the x switch, okay? So the original function, f of x is the what? For a person x inches tall, so let's read it. Right. So for a person x inches tall with a sprained ankle, the length of the crunches in inches that he or she may need is approximated by this function. So x is how tall, and then the y value, or f of x, is the length of the crutches. Okay? So on the inverse, what is the x going to be?
48 minus 2.
Well, so since we're trying to figure out, so it's kind of asking more of a conceptual question. Just think about, so if the x is the inches tall for the original function, and the y is the length of the crutches, on f inverse of x,
The x will be the length of the crutch.
x is the crutches, and f of x, or f inverse of x, let's just say y, is the height of the person. Okay? Okay, so they switch. So given that, which of the answers would make the most sense? Okay, so it's saying interpret the meaning of f inverse of 48 equals 50. So the 48 here would represent what? Okay, right, right, right. Okay, so if the crutches were, so the input would be the length of the crutches, okay, and the y would be the height, okay, so that would correspond to, is it D? Crutches that are 48 inches long are appropriate for a person that is 50 inches tall, okay, D, right? Okay, so again, the relationship there is really about xy versus yx, okay, all right, so that's a good question. All right, we're going to skip to 81. Okay, just trust me with this, right? So let's skip down to 81, right? Just because we have about 20 minutes, and I want to definitely get to the exponential and logs, because I'm sure that you guys have questions on that. Okay. Okay. All right. So for the exponential function, f of x equals 3 times 1.5 to the x, we want to evaluate f to the negative 1, all right? Okay. So what I'm saying is that I'm looking for 3 times 1.5 to the negative 1, all right? Certainly could type it into your calculator, not in the graphing function, just in the regular scientific part, okay? Or you could say 1.5 is the same as 3 halves, right? Okay? Right? Okay? And so 3 halves raised to the negative 1 is what? 2/3. It's the reciprocal. Okay? And so then I have 3 times 2/3, which is just 2. Okay? So D. All right? Okay? You just want to be careful sometimes when you're using your calculator, especially if you do some rounding or something like that, you may or may not come out with one of the solutions that's given, and you just want to be sure. I mean, in this case, you probably would come out with 2, but you want to just be careful about that. Okay? All right. Okay. 82, similarly, we're evaluating the function at 1/2. So f of 1/2 is going to be 4 to the 1/2, which is the same thing as the square root of 4, which is just 2. Okay? All right?
So if it was 4 to the power of 1/3, would it be the same thing as the cube root of 4? Okay.
Yes. Okay? Negative and fractional exponents. Okay? All right. Take a look at question. You want to, okay. This one? Okay. So let me just say, before we go to the next one, make sure you take a look at the graphs of exponential functions and logarithmic functions, okay? You should at least be able to identify the difference when the base, in both cases, is greater than 1 or less than 1, okay? So that, because those should be easy questions for you too. All right. Okay, so let's look at this one. Here we're talking about an exponential function, y equals 4 to the x, and we want to know which of the following statements is not true. Okay? And this can be, I mean, we can generalize to all exponential functions in this case, but we'll just focus on 4 to the x. Okay, so 1, that the domain is from negative infinity to infinity. Is that true?
Yes.
Yes, because I can raise 4 to a positive or negative power, right? It doesn't matter. It wouldn't change. So that's good. But the range is only going to be positive. I can't raise 4 to any value that would then give me a negative value, right? So the output, or the y, is always going to be positive. It's not going to be 0, right? Okay? Because basically this is saying, 4 to what power will give me 0, right? There is no exponent. I can't raise 4 to any power that could be true.
What
So,
about 4 to the power of 0?
4 to the power of 0 is 1.
Okay.
Okay? And 4 to the negative exponents are what?
1 over 4.
Right, well, then they're the fractional parts, right? Because we just saw 4 to the 1/2 would be 2, right? Okay, and then 4, I'm sorry, negative, right? So 4 to the negative 2 would be, or 4 to the negative 1 would be 1/4, okay? So the range is positive. The y-intercept is 0, 1. It's true, right? Because when I plug in 0 for x, you get the y value would be 1, okay? So 4 to the 0 is 1. The graph passes through the point 2, 6. Okay, so that would mean 4 raised to the second power would be 6. Is that true?
No.
No. Okay. So right. So the answer is actually D. Okay. There is no x-intercept, basically because if that were true, then the y value would be 0, and we saw that that's not true. And the graph passes through the point -1, 1/4, and that is true. Okay. So these are both true. All right. Okay. So with 84, same thing. If you kind of come into the final exam having an idea of what an exponential function, the graph of an exponential function looks like, where the base is greater than 1 and where it's less than 1, these questions will be very easy for you. Okay? All right? So one thing to know, first of all, it's only going to be, the two choices are A and C, right? These are graphs of logs. Okay? So you want to, I'm saying it's good for you to kind of go and see examples in the book so that you can kind of, because this question would come out really easy. Because now the question is basically, is the function increasing or decreasing? Okay? Okay, so one way to do about it is to think about some of the points. Okay? So let's take a point over here. So at -1, this looks like this point is up here versus at -1, you're talking about something that's below 1. Okay, so here the y value is greater than 1. Here the y value is lower than 1. What happens if I take f of -1 of 1/3? Okay, so if I raise 1/3 to the -1, what happens to that? What do I get?
3.
3. Okay, that means that there is a point -1, 3 on the graph. All right, so which one would that be? A, right? Okay, because see, this point here, so if this is the point 0, 1, all right, then this is the point -1, 3, okay?
Because 1/3 is less than 1.
Exactly.
So
This
if it
is
were 2 raised to the power of x, then it would have been D.
C, okay? Go back and look at, this is what I'm saying, go back and look at that section and look at some of the graphs. So the difference is between, okay, so,
Logs in that.
Okay, look at, so this one, the key is, the other thing is too that I know, is that for an exponential function you always have the point 0, 1, no matter what the base is. For a logarithmic function you always have the point 1, 0 because they're inverses of each other. Okay, all right? Okay, so I'm just going to keep saying this. Go back and look and see what the graphs look like in the case where A is greater than 1, A is less than 1. Okay?
What did you say exponential functions always have the point of?
Mm-hmm.
Exponential is -1, 0.
No.
Okay, these two functions. All right?
Move the paper up.
No, is it 0, 1 or
Okay, so an exponential function, the point is 0, 1. Okay? Because the log function is the inverse of it, the corresponding point is 1, 0. All right? Okay?
-1 and log is 1, 0.
Okay? Just see how many more we've got to get in here. All right.
I think that's right.
Okay?
I have a question about that real quick. If A is the answer to number 84, and you said the exponential function always has the point 0, 1 or 0, negative 1?
0, 1.
Okay.
Okay?
And then the log is 1, 0.
Okay? So, again, in this case, I mean, this is the same choices, right? But now we're asking about the inverse, or the log base 2 of x, okay? So let me just say here, because this will help us with the other problems, all right? Okay? If you have this function and this, the relationship between them is that they're inverses. But if log base a of, let's just say, b is equal to k, then a to the k is equal to b. All right? These two things are related. Okay?
Yeah, can you
Sorry.
So since it's a log, you know it's going to be B or D on the graph.
Exactly. Okay. So, hold on. Let me just put this up here because this is going to help. Oh, my gosh. Sorry. Okay. All right. You want to make sure that you have that relationship down. Okay. Okay. The relationship between the log and the exponential. All right. You want to make sure that you can identify the graphs. Right, so for example, in number 85, all right, I know that my choices are either for this. All right, hold on, I'll put it back up. Hold on, let's go through this one real quick. All right, log base 2 of x. Since I know that these two are exponential functions, then my choices are b and d. All right. The way I would figure out between if it's b or d is, again, I could look at a point. And I could say, all right, well, I know the point 1, 0 is there, okay? So now let me see what happens at, for example, 2, okay? X equals 2, all right? Because if you notice, on this graph where x equals 2, the y value is negative. On this graph, it's positive, all right? So log base 2 of 2, I'll pull it up, is equal to what? Does anybody know what log base 2 of 2 is equal to? It's 1, okay? Because this is related to, so we call this, let's say we'll call it k. The way we solve this is we say 2 to the k is equal to 2, sorry. Ugh, 2 to the 2 is equal to 2. So this would have to be 1, okay? So k would be equal to 1. So this corresponds to the point 2, 1, all right? So this point would be on the graph of log base 2 of x, so that tells me that it's b, all right? Okay. Right? Okay, I know that because I know this is kind of like probably the last bunch of stuff you guys did in the semester, and you probably want to spend some time looking on this between now and the final. Yeah, so the answer for that one's B, okay? So let me go on through the next few just so that we can get in a couple more of these before the review ends. And then I'll hang around for a while if you have specific questions, okay? I know that we're here. Okay, so here we want to know, which of the following functions is graphed here, okay? So again, this looks like an exponential function, so I'm going to count out C and D. And now my question is it A or is it B? All right, well, I have a point 2, 4 here. So when x is 2, y is 4, so that would correspond to which one? A. Okay, all right? Okay. So again, make sure that you get a chance to look at all of those. All right, so let's do some of these log functions, these log problems. And then I don't know how much more we'll have time to do, okay? All right, so which equation is equivalent to 3 to the negative 2 equals 1/9? All right, again, you have to know this relationship. Log base A of B equals K is related to A to the K equals B, okay? Okay? So the base here would be what? So we're talking about 3, all right? So this would be log base 3 of 1 over 9 is equal to negative 2, okay? Or C, all right?
That looks very strange, like on C, because 1 over 9 doesn't look like an exponent. It looks like a base.
This is the base,
Right.
okay? Right? And the exponent here is negative 2, okay? So but it just comes from this relationship, right? Okay? All right. We're going to skip 88. Let's look at 89, because 88 is a little bit more of the same, all right? So let's look at 89. Okay, so now we're going the other way. So now we have logs, and we want to know what the exponential form would look like. Okay, again, using that same idea, log base A of b equals k is related to a k equals b. I know that this is related to 2 to the x is equal to 3. Okay, this one's a little funny. It's supposed to be log 2, base 2 of x, but so it would be, in this case, 2 to the 3 is equal to x. Okay? All right? All right, just hang in there with me. You guys are done. Okay. All right. So now we're going to actually evaluate some of them. All right. Okay. Okay, good. So I think we'll make it. All right. So here, again, I'm looking for the value k such that 3 to the k is equal to 27. All right? Because I know the relationship between the log function and the exponential. Okay? So what does the value k, what would it have to be? 3. Okay? All right? So in this case, log base 3 of 27 is equal to 3. All right? Here, same thing. 5, this relates to 5 to the k equals 25. So that tells me that k has to be 2. Okay? All right? Log base, so when it's just log and you don't see a base, then it tells you that it's log base 10. Okay? So this is the same thing as log base 10 of 1 over 10. So I want to know 10 to what power is equal to 1 over 10, which tells me k is equal to negative 1. Okay? All right? Okay, and then similarly, natural log of 1 is the same thing as log base e, right? That magical number.
Can you say that natural?
It's natural log of 1. Okay, so then the related exponential function would be e to the k equals 1, and so k would be 0. Okay?
So if you were to ever have, for instance, log 1 over 15, then it would just be 1 over 15. Right?
Okay, log base, say it again.
Like if you were to have, would you have always 1 over 10? I mean, I've seen that before, but would it be a different number? Would it be like 1 over 15 or 1
Well,
over
I mean, okay. So you could do things that have, so for meaning if this was log of 1 over 15,
Yeah.
but you would have to, you wouldn't be able to, you wouldn't come up with that on your own.
Oh.
So problems like this, you would be given nice exponentials.
Okay.
Okay? All right. So we're going to skip 91. It's more of the same. Okay? Let's look at 92, though. Find the value of x if log base 3 of x equals negative 2. So what would be the related exponential equation? Okay, so the related exponential equation would be 3 to the negative 2 is equal to x. And so then that tells me x is equal to what? 1 over 9. Okay, right? Because this is equal to 1 over 3 squared, so it would be equal to 1 over 9. All right. Okay, so let's skip to 90. I think 93 and 94 are similar, just plays on this, okay? The main thing is being able to come up with the exponential equation that goes with it, all right? So definitely look at some of those, but I want to skip to 95 so that we have a chance to look at the logarithmic expressions, okay? All right. Okay. So here you'd have to use those properties of logarithms, okay? Right? And so I'm not going to list them all, but you want to go back and look through those. Okay, so because we're dividing here, I know that this is the same thing as natural log of x squared minus the natural log of y to the fourth. Okay, I wrote that a little close, so I'll put parentheses. Okay, all right? Okay, so just, you want to make sure that you look at the properties for that. All right, and then so now this is the same thing as 2 natural log of x minus 4 natural log of y. Okay, and so you have problems where you're either needing to expand the expression or compress it, right? So in this case, this would be fine. You would leave it like this. I mean, maybe put a parentheses around it. Okay. All right, and then 96 has this going the other direction. Okay. So now we want to compress.
So
Right.
the answer for 95 is 2 natural log of x minus 4 natural log of y.
Right, that's all you can do. Okay, so for these, you're not going to just get a numerical answer. You're just trying to rewrite it so that you, using the properties, right? Okay, same thing here. What I would do is start with the exponent. So this would be log of x plus 1 to the 1/2 plus log of x minus 1 to the 1/2. Okay, and so that's equal to, I'm just going to rewrite it as the square root of x plus 1 plus the log of square root of x minus 1. All right? And then based on the properties of logarithms, I know that this can be condensed into this, where I'm multiplying the two expressions, right? Okay? And so I think, if you can combine it even more so that you have the square root of x squared minus 1. Okay? So that's where they get the answer from in the back. But the main idea being that you can use the properties and combine it. Okay? So know the properties, being able to go backwards and forwards. All right. We're going to do 97 and 98, and then we're going to do. Okay. 97 and 98 are about solving equations using logarithms. The main thing here is remembering the inverse, right, relationship. The same way that you would take the square root of x squared to solve an equation with x squared, you would use the inverse. 10 to the x, the inverse of it is log base 10. Okay, so what I would do is take the log of both sides, taking the log because log is base 10, right? When it doesn't have anything written there. And then so what happens on the left side? This is like applying the inverse to the function, and we know when you compose those two, you just get x, and so the solution is log of 50, okay, or b. Okay. All right. Okay, similarly with 98, we know the inverse of that function is natural log. So I can take the natural log of both sides. Okay. And if I do that, again, taking the natural log of e to the x plus 2, it acts as identity. And so I get x plus 2 on this side, natural log of 50 on this side. And so x is equal to natural log of 50 minus 2. Okay? All right. I think we're going to be booted, so we're going to have to head out. We gotta go? Okay. Huh. Yeah, I'll be outside. I'll wait outside for a little bit. Okay, so, we have to get out of here. So we need to pack up and get all of our stuff out. But okay? All right, good luck.